The Challenger disaster was not simply a sudden mechanical failure in the sky. It was the visible endpoint of warnings that had already moved through engineering memos, launch constraints, teleconferences, and the cold metal of Kennedy Space Center. That is the uncomfortable fact at the center of this record. On the morning Space Shuttle Challenger rose from Launch Complex 39B, the public saw a launch. NASA saw the 25th mission of the Space Shuttle program beginning at last. Many watching saw a national classroom, a crew of 7, and another step in making spaceflight appear routine. But behind that image was a machine whose most vulnerable seal had already been the subject of concern, disagreement, and documented damage on earlier flights. The question is not whether anyone knew the future. They did not. The question is narrower and more difficult. How did a known vulnerability in a solid rocket motor, field joint, remain acceptable long enough for Challenger, orbiter OV-099, to lift off into conditions that made that vulnerability worse? At Kennedy Space Center in Florida, January 28, 1986, had already become an unusual launch morning. A severe cold wave had reached the Cape Canaveral area. Ice was visible at the launch site. The shuttle stack stood at Launch Complex 39B, the orbiter Challenger attached to its large external tank, with 2 solid rocket boosters on either side. Those boosters were not background hardware. For the first 2 minutes of flight, they would provide the enormous thrust needed to pull the shuttle away from Earth. At 11:38 a.m. Eastern Standard Time, mission STS-51L lifted off. The ascent began with the familiar violence of a shuttle launch. The solid rocket motors ignited, the hold-down posts released, and Challenger climbed from the pad. To viewers, the early seconds looked like the beginning of another successful flight. Mission control communications continued. The vehicle rolled onto its planned trajectory. The launch commentator's voice remained measured, following altitude, velocity, and downrange distance as if the flight were entering the normal language of procedure. But the accident investigation would later focus on something that happened almost immediately. The Presidential Commission, chaired by William P. Rogers, later known as the Rogers Commission, reported that smoke was observed from the aft field joint area of the right solid rocket booster between about 0.678 and 2.5 seconds after solid rocket motor ignition. Those smoke puffs appeared before the vehicle had truly become a distant object in the sky. They were coming from the region that would later be identified as central to the failure. A little less than a minute into flight, another sign appeared. At about 58 seconds, a flame from that same right booster joint area became clearly visible. It was not merely exhaust in the ordinary path of a rocket. It was evidence that hot combustion gases had escaped where they were supposed to be contained. At 73 seconds after liftoff, Challenger broke apart. All 7 crew members were lost. Francis R. Scobie, Michael J. Smith, Judith A. Resnick, Ellison S. Onizuka, Ronald E. McNair, S. Krista McAuliffe, and Gregory B. Jarvis. The mission that had been planned as Challenger's 10th flight and the Space Shuttle program's 25th became the program's defining catastrophe. In the first public shock, the image seemed almost impossible to process. A bright plume, a branching cloud, pieces of the vehicle moving away from the path where the orbiter should have continued upward. The language available in the moment was incomplete. Something had happened. The flight had not survived. But the cause was not visible in full from the television picture. The deeper record would come from recovered hardware, photography, testimony, and engineering history. NASA identified the accident cause as an O-ring failure in the right solid rocket booster, aggravated by extreme cold weather in Florida before launch. The Rogers Commission stated the immediate cause with more specific mechanical focus: failure of the pressure seal in the aft field joint of the right solid rocket motor. That phrase, pressure seal, is quiet compared with the scale of the disaster. But it is the key to the whole episode. Inside the solid rocket motor, hot combustion gases had to remain contained. The field joint was built from metal parts known as tang and clevis, with zinc chromate putty and 2 rubber O-rings intended to prevent those gases from escaping. The design depended on the seals doing their job instantly, under violent pressure, vibration, and movement. If the seal did not work in time, hot gas could pass the O-ring. It could erode rubber. It could create a path. It could become, in seconds, a failure large enough to destroy the vehicle. The Rogers Commission did not describe the field joint as a simple part that happened to fail once. It found the joint design unacceptably sensitive to temperature, physical dimensions, material behavior, reuse, processing, and dynamic loading. In other words, the joint's ability to seal was not controlled by one clean variable. It depended on a combination of geometry, rubber behavior, manufacturing and processing history, and the forces of ignition. That finding matters because disasters are often remembered as moments, while their causes are usually chains. Challenger's destruction occurred 73 seconds after liftoff, but the warning signs did not begin at 70 seconds or at 58 seconds, or even at ignition. Earlier shuttle flights had shown O-ring erosion, blow-by, or soot. Significant concerns followed STS-51C in January 1985 and STS-51B in April 1985. After STS-51B, a launch constraint was placed on STS-51F in later flights, including STS-51L. That constraint was repeatedly waived. Inside Morton Thiokol, the contractor for the solid rocket motor, engineers had put concerns into writing. On July 31, 1985, Roger Boisjoly wrote an internal memo titled SRM O-ring erosion / potential failure, criticality. He warned that failure to prioritize the field joint O-ring problem could risk losing a flight and launch pad facilities. On October 1st of that same year, Thiokol engineer Robert Ebeling used the word help in a report describing delays and lack of support for the SEAL task force. Those were not predictions of the exact morning, crew, or sequence of events. They were warnings about a known system. They belonged to the same mechanical family as the failed joint later recovered and examined after Challenger was lost. The cold made the warning sharper. The Rogers Commission reported that cold O-rings lost resiliency. A compressed O-ring at 75 degrees Fahrenheit returned to shape about 5 times faster than one at 30 degrees Fahrenheit. On the night before launch, Thiokol engineers and NASA personnel discussed forecast temperatures at Kennedy Space Center that were far below the previous flight experience base for O-ring temperature. Thiokol's initial engineering recommendation was not to launch below the prior O-ring temperature experience base of 53 degrees Fahrenheit. And yet, after a management caucus at Morton Thiokol, that initial no-launch recommendation was reversed. A written recommendation supporting launch was sent. The countdown proceeded. The Rogers Commission later stated that the launch decision was flawed and based on incomplete and sometimes misleading information. It also found that Level 1 and Level 2 NASA officials were not told about the launch constraint, the reasons behind it, or the series of waivers before STS-51L. That is one of the most important organizational facts in the case. The problem was not only the behavior of rubber in the cold. It was also the movement of information inside a large technical institution. On the pad, none of that history was visible to the television audience. Launch Complex 39B looked like the stage for another shuttle ascent. Challenger's name carried years of previous missions. The shuttle program had been built around the promise of repeated flights, operational confidence, and a future in which space access would become more regular. STS-51L was part of that schedule, part of that public story, part of a year in which NASA planned an ambitious sequence of shuttle missions. But the machine that rose that morning carried more than payloads. It carried the accumulated consequences of accepted risk. The archive record asks us to look at the disaster without reducing it to a single villain, a single meeting, or a single frozen morning. The cold mattered. The O-rings mattered. The field joint mattered. Earlier erosion mattered. Memos mattered. Waived constraints mattered. Communication failures mattered. Each detail becomes more significant when placed beside the others. That is why the first image of Challenger lifting off is so difficult to separate from what came before it. The vehicle appeared to be leaving Earth in the ordinary rhythm of a launch. In fact, it was entering the final seconds of a failure whose warning signs had been present long before the flame became visible. At the center of the public memory are 7 people, strapped into a spacecraft that represented skill, discipline, science, teaching, military experience, engineering work, and national ambition. Their mission drew unusual attention, not only because it was a shuttle flight, but because it was meant to be seen and understood by the public in a new way. To understand why STS-51L mattered so deeply before it failed, we have to look next at the crew, the mission they were assigned to fly, and the human story that made the technical warnings even harder to ignore. The public story of STS-51L began with 7 names, spoken in NASA briefings, printed in mission materials, and repeated across classrooms and newsrooms before the launch. Francis R. Scobie, Michael J. Smith, Judith A. Resnick, Ellison S. Onizuka, Ronald E. McNair, S. Krista McAuliffe, Gregory B. Jarvis. They were not symbols when they climbed aboard Challenger. They were the assigned crew of a specific NASA mission, scheduled within a crowded shuttle program, flying a particular orbiter, carrying particular payloads, and representing several different strands of the American space effort. But, because of the way this mission was presented to the public, their faces and names reached far beyond the normal audience for a shuttle launch. STS-51L was planned as the 25th mission of the Space Shuttle program and the 10th flight of Challenger, NASA orbiter OV-099. By that point, the shuttle had become part spacecraft, part national infrastructure, and part public demonstration of routine access to orbit. The missions were complex, dangerous, and technically demanding, but they were increasingly described in the language of schedules, payload assignments, and operational rhythm. Challenger's flight was supposed to fit into that rhythm. The crew list reflected that operational confidence. Francis R. Scobie, Michael J. Smith, Judith A. Resnick, Ellison S. Onizuka, Ronald E. McNair, S. Krista McAuliffe, and Gregory B. Jarvis were assigned to a mission that combined communications work, astronomy, and public education. The planned payloads included TDRS-B, part of NASA's Tracking and Data Relay Satellite System, and the Spartan Halley astronomy satellite, intended to observe Halley's comet. These were not background details. They show how the shuttle was being used to carry satellites, support science, and make spaceflight appear connected to both national systems and public curiosity. The most visible part of that public connection was Krista McAuliffe. The teacher and space activities planned for the mission would have included live lessons during the flight. That plan changed the audience. A shuttle launch that might otherwise have been followed mainly by space reporters, NASA employees, contractors, and enthusiasts became a classroom event. Students and teachers had a reason to watch, not just because a spacecraft was launching, but because one of their own professions had been placed inside the mission. This mattered because STS-51L was not only being launched, it was being shared. It carried the image of access, participation, and national confidence. The mission suggested that the shuttle was mature enough to carry a teacher into orbit and bring lessons back to Earth in real time. It suggested that the spacecraft was no longer only a machine for test pilots, military specialists, scientists, engineers, and professional astronauts. It was being presented as a vehicle that could connect ordinary civic life to space. That public meaning did not erase the technical mission. TDRS-B and Spartan Halley were part of the assigned work. The shuttle was still a launch vehicle, an orbiter, a payload carrier, and a complex system supported by NASA centers across the country. Kennedy Space Center in Florida handled launch operations. Johnson Space Center in Houston was central to crew and mission operations. Marshall Space Flight Center in Huntsville had major responsibilities tied to the solid rocket boosters. NASA headquarters oversaw the larger agency program. Morton Thiokol, with major engineering work at its Wasatch plant in Utah, was the contractor for the solid rocket motors. In public, however, most of that institutional map was invisible. Viewers saw Challenger on the pad. They saw the crew. They saw the countdown. They heard about a teacher going to space. They did not see the full chain of engineering review, contractor concern, launch constraints, waivers, and temperature discussions that had been developing behind the scenes. That separation between the visible mission and the internal record is one of the essential tensions in the Challenger story. The public attention around Krista McAuliffe also shaped the emotional record after the disaster. But before the launch, it shaped expectation. The planned live lessons made the mission feel personal to schools across the country. The presence of a teacher aboard Challenger made the shuttle program seem close, understandable, and open. NASA's language of access to space had found a human form. The mission was still part of a disciplined flight schedule, but it carried a kind of civic theater that most shuttle flights did not. That made the technical warnings harder to see from the outside. A launch watched by classrooms can look like a national moment of trust. But trust in spaceflight rests on materials, procedures, and decisions that are not visible on camera. It rests on whether a seal closes when it must close. It rests on whether engineers' concerns travel upward with enough force. It rests on whether the experience of earlier flights is treated as a warning or as reassurance. By January 28, 1986, the shuttle program had already flown missions that left marks in the engineering record. Earlier flights had shown O-ring erosion, blow-by, or soot. The right way to understand STS-51L is to hold both records at once. There was the public record: 7 crew members, a teacher in space, a communication satellite, a Halley's Comet astronomy payload, a shuttle mission in a busy national program. And there was the technical record: repeated signs that a solid rocket motor field joint sealing system was not behaving as safely as it needed to behave. The crew did not create those conditions. Their place in the story is not as evidence in an engineering case, but as the human consequence of it. Francis R. Scobie, Michael J. Smith, Judith A. Resnick, Ellison S. Onizuka, Ronald E. McNair, S. Krista McAuliffe, and Gregory B. Jarvis entered a vehicle built and cleared through a system of design assumptions, contractor judgments, NASA reviews, and launch decisions. Their mission was the point where all those systems met. This is why the public mission matters in a documentary account of the warning signs. It explains why so many people were watching. It explains why the disaster became a shared memory almost instantly. But it also sharpens the central question: how could a mission with such visibility proceed while serious concerns existed inside the engineering record? The answer is not found in the crew cabin. It is found lower in the stack, in the booster hardware that had to perform before Challenger could ever become a spacecraft in orbit. Each solid rocket motor contained field joints that had to seal under violent conditions at ignition. Metal parts had to hold their geometry. Putty, insulation, and rubber seals had to prevent hot combustion gases from escaping. The public saw a vehicle rising cleanly into the sky. Inside one of its right booster joints, the mission depended on a small sealing system doing its work instantly, under pressure, in cold conditions, with no margin for delay. The public mission depended on a private mechanical promise that the booster joints would seal before fire could find a path out. It was a small promise compared with the size of the shuttle stack, but it was absolute. At ignition, each solid rocket motor became a controlled furnace, producing hot combustion gases under enormous pressure. Those gases were supposed to go one way, down through the nozzle, helping lift Challenger away from Kennedy Space Center. They were not supposed to escape sideways through the seams where the motor segments had been joined. The Rogers Commission later identified one of those seams as central to the accident: the aft field joint of the right solid rocket motor. To understand why that phrase mattered, it helps to slow down and look at the machine as a set of fitted parts rather than as a single white booster seen from a distance. The solid rocket motors were built in segments. Those segments had to be transported, assembled, and connected into a full motor. Where one segment joined another, the connection was called a field joint. It was not an abstract design feature. It was a physical circular joint running around the booster, formed by metal parts that fit together. One side included a tang. The other included a clevis. The tang fit into the clevis, creating a joint that was meant to hold structure and preserve a pressure seal during the violent first moments of motor operation. The joint was not sealed by metal contact alone. Inside the joint system were layers and barriers, each with a role. Zinc chromate putty was used as part of the sealing arrangement. 2 rubber O-rings were installed in the joint, a primary O-ring and a secondary O-ring. The terms sound simple, almost ordinary, but in the accident record, they became essential words. The primary O-ring was the first pressure seal. If the joint behaved as intended, pressure inside the motor would help push that O-ring into position. This was known as pressure actuation. The seal was not merely sitting there like a static gasket in a household pipe. It had to respond to the sudden rise of pressure at ignition. It had to move, deform, and seat itself quickly enough to block the path of hot gas. Behind it was the secondary O-ring. The purpose of the second ring was redundancy, a backup seal if the first one did not perform as intended. But a backup in this system still depended on geometry, pressure, timing, and material behavior. It was not magic. It could not protect the vehicle if the joint opened in the wrong way, if the O-ring did not move fast enough, or if hot gas and combustion debris damaged the sealing path before the rubber could do its work. The hazard was blow-by, hot gases passing the primary seal. If combustion gases slipped past the primary O-ring, they could erode the rubber. That damage is called blow-by erosion. The word erosion can sound gradual, like weather wearing stone. In this setting, it meant a far more urgent process. Hot gas under pressure could cut, burn, or remove material from the O-ring. Once that happened, the seal was no longer simply delayed. It was damaged. Another term in the record is impingement erosion. This refers to the effect of a directed stream of hot gas striking a material. If gas found a channel through the joint and impinged on the O-ring or nearby insulation, it could concentrate damage in a local area. The point is important because the joint did not have to fail everywhere around its circumference. A local path could be enough. One place where hot gas escaped could grow into a burn-through. The joint also included insulation. The research record identifies NBR insulation as one of the materials involved in the motor joint system. NBR refers to nitrile butadiene rubber, a rubber material used for insulation. Its role was to help protect the metal case and joint region from the environment inside the motor. The motor's combustion was not clean in a gentle sense. It produced intense heat, pressure, and debris, including aluminum oxide combustion debris. That debris could affect the seal environment. It could be part of the material moving through any leak path. It could contribute to the harsh conditions the O-rings and insulation had to survive. All of this mattered because the seal had to happen immediately. The first seconds after solid rocket motor ignition were not a period of calm adjustment. The structure was loaded. Pressure rose. Parts flexed. The joint could change shape under load. One of the crucial behaviors was joint rotation. As internal pressure built, the tang and clevis did not remain perfectly fixed in their original relationship. The joint could rotate slightly, changing the gap the O-ring had to seal. This tang to clevis gap is one of the quiet mechanical details behind the disaster. The O-ring sat in a groove and had to seal across the space created by the joint geometry. If ignition caused the joint to open or rotate, then the O-ring had to follow that motion fast enough. Pressure actuation was supposed to help, but the O-ring's ability to respond depended on resiliency, the capacity of the rubber to return toward its shape after being compressed. Resiliency is not a decorative property. It is the difference between a rubber seal that springs into place and one that remains slow, stiff, or flattened when it is needed most. Engineers describe rubber behavior using several measures, including shore hardness. Shore hardness is a measure of how hard or soft a rubber material is. A harder or less resilient O-ring may not respond in the same way as a softer, more elastic one. Temperature can change that behavior. So can age, manufacturing variation, compression history, and the conditions of the joint. The Rogers Commission would later emphasize that the joint was unacceptably sensitive to a range of factors, but even before reaching that larger finding, the basic mechanical issue is clear. The seal depended on rubber moving quickly inside metal parts that were themselves moving under pressure. The zinc chromate putty was intended to help protect the O-rings from direct exposure to combustion gases. In theory, it formed a barrier in the joint, but it was not the final pressure seal. If the putty allowed a path, or if pressure effects created a pathway through it, then the O-rings became the critical defense. The primary O-ring had to seal first. If it failed to seal, the secondary O-ring had to be capable of sealing before hot gases caused irreversible damage. The accident record shows why this system became the focus of investigation. The Rogers Commission concluded that the cause of the Challenger accident was failure of the pressure seal in the aft field joint of the right solid rocket motor. That statement is precise. It does not say the entire booster suddenly exploded without warning. It points to the pressure seal in a specific joint, in a specific booster, in the aft field joint region. The fatal event began with a failure of containment. On the launch film, the earliest evidence would later be found in the form of smoke from the right solid rocket booster aft field joint area shortly after ignition. But the chapter we are in now sits just before that visible evidence. It is concerned with the design logic that made those first instants so important. The gases inside the motor were always seeking escape. The field joint's purpose was to deny them a route. Metal, putty, insulation, and rubber All had to cooperate under sudden load. The phrase, two O-rings, can give a false sense of comfort. Redundancy sounds safe. But redundancy only works when the backup is protected from the same conditions that defeated the first barrier, and when it has time and geometry to function. In the field joint, the primary and secondary O-rings were not isolated from the same joint rotation, the same pressure rise, the same tang and clevis movement, and the same temperature-dependent rubber behavior. If the joint gap opened too much or too fast, both seals could be placed at risk. This is why later discussions about Challenger did not remain at the level of one broken part. The O-ring was the visible focus, but the seal was a system. The aft field joint included the hardware that set the gap, the putty that shaped the gas path, the insulation that faced combustion products, and the rubber rings that had to respond. A defect in understanding any one of those elements could distort the risk of the whole assembly. For engineers at Morton Thiokol and NASA, this was not merely a question of whether rubber could burn. It was a question of whether the joint could maintain pressure integrity during the ignition transient. That word, transient, matters because the most dangerous condition could occur before the system had settled into its operating state. The seal had to form while the motor was coming alive. It had to work while loads changed rapidly, while the structure flexed, and while combustion pressure forced the hardware into its real flight shape. The field joint therefore demanded both strength and timing. The metal case had to hold. The tang and clevis had to fit. The putty had to prevent hot gas from reaching the O-rings. The O-rings had to be resilient enough to move and seal. The secondary O-ring had to remain a real backup, not just a drawing board assurance. And the entire arrangement had to perform around the circumference of the booster, including local regions where loads and geometry might not be uniform. That last point will become increasingly important. The Rogers Commission did not treat the joint as sensitive to only one condition. It found that the design was vulnerable to temperature, physical dimensions, material behavior, reuse, processing, and dynamic loading. The aft field joint was not a simple ring in a simple groove. It was a changing mechanical boundary under pressure, and small differences in gap, stiffness, or timing could decide whether the seal closed before hot gas passed it. So the warning signs before launch begin here, inside the machine's smallest critical spaces. Challenger's right booster did not need a large opening to begin failing. It needed only a path where combustion gas could move faster than the seal could respond. Once that path existed, blow-by, erosion, debris, and heat could turn a delayed seal into a damaged one. The question then becomes sharper. What made this joint so sensitive, and why did its geometry leave so little room for hesitation at ignition? The question becomes sharper because the joint was not waiting passively for pressure to arrive. At ignition, it moved. The metal case of the solid rocket motor flexed under load. The tang and clevis, already separated by small physical clearances, could open farther for a brief but critical moment. In that moment, the primary O-ring had to change from a seated rubber ring into an active pressure seal. It had to move quickly enough and recover its shape quickly enough to block a route that hot combustion gas was trying to enter. The Rogers Commission did not describe the solid rocket motor field joint as vulnerable to a single weakness. Its finding was broader and more troubling. The joint was unacceptably sensitive to temperature, to physical dimensions, to the behavior of its materials, to reuse, to processing, and to dynamic loading. In other words, the seal did not depend only on whether an O-ring existed in the groove. It depended on a chain of conditions being favorable at the same time. That chain began with geometry. The field joint connected large cylindrical motor segments. One segment carried the tang, a projecting metal edge. The other carried the clevis, a receiving metal fork. When the joint was assembled, the tang fit into the clevis, with O-rings positioned to seal against gas trying to travel through the joint. But the fit was not a perfect, motionless closure. There was a tang to clevis gap, and that gap mattered because it helped define how far the O-ring had to move, how well it was squeezed, and how quickly it could become an effective seal after ignition. In a static drawing, the joint could look orderly. Metal nested into metal. Putty placed ahead of the seals. A primary O-ring and a secondary O-ring standing guard behind it. But the Commission's concern was not only the drawing. It was what happened when the solid rocket motor came alive. During ignition, internal pressure rose rapidly. The booster case responded to that pressure. The joint rotated. The gap between the tang and clevis could open. The O-ring, which had been compressed in its groove, had to follow that movement and seal the newly opened space before combustion gas could pass. That is why timing was central. The field joint did not merely need an O-ring that could seal eventually. It needed an O-ring that could seal almost immediately under violent startup conditions. A delayed seal was not a small inconvenience. It could become the beginning of blow-by, where hot gases moved past the O-ring. Once gas moved through, it could erode rubber, carry hot particles, and change the joint's condition before the seal had fully performed its job. The Commission's language about sensitivity is important because it shows how little margin existed. Physical dimensions affected the initial squeeze on the O-ring. If dimensions left a larger gap or reduced compression, the O-ring had more work to do. Material behavior affected how quickly the rubber could respond. Reuse and processing could influence the condition of the metal parts, insulation, putty, and seals before flight. Dynamic loading affected how the joint changed shape under real launch forces, not just how it appeared during assembly. The result was a design that could be pushed toward danger by several modest effects at once. A slightly unfavorable dimension might not by itself guarantee failure. A processing variation might not by itself guarantee failure. A change in material response might not by itself guarantee failure. But the system was sensitive to all of them, and at ignition, they could combine at exactly the wrong time. The tang-to-clevis gap is one of the clearest examples. If the gap opened during motor pressurization, the O-ring had to maintain contact while the surfaces around it were moving away. The O-ring was meant to be pressure actuated. Gas pressure would help push it into a sealing position. But that idea contained a risk. For pressure to actuate the O-ring, pressure first had to reach it. If the O-ring was slow to move, or if the gap opened faster than the rubber could respond, hot gas could move along the joint before the intended seal was fully established. This was not an abstract engineering debate after Challenger. The Rogers Commission identified the failure as the pressure seal failure in the aft field joint of the right solid rocket motor. The same family of details, the joint geometry, the O-ring response, the movement at ignition, became central to understanding why the accident could happen. The seal had to work in the first moments when the motor was coming up to pressure and the joint was being forced into a new shape. The right booster also had a local feature that made this discussion more specific. The external tank and the right solid rocket booster were connected by struts. One of those connections was near the 310-degree position, close to the aft field joint. Around the circumference of a booster, position mattered. The joint was not necessarily stressed in exactly the same way at every degree around the ring. Loads could be local, and local effects could change how much a gap opened in one region compared with another. The Rogers Commission reported that the 310-degree strut region could increase local joint gap opening by about 10 to 20%. That figure matters because it turns a general design sensitivity into a local mechanical concern. If the joint was already vulnerable to gap opening at ignition, then a region that opened more than the surrounding joint could be a more demanding place for the O-ring to do its job. The rubber would have to respond not to an idealized average opening, but to the actual opening, where the local hardware and loads made the situation worse. This region was also close to the area later associated with the right booster aft field joint failure. The flame location was estimated around 305 to 307 degrees on the right booster's aft field joint, and recovered fragments showed large burn-through holes from about 291 degrees to 318 degrees. Those facts do not require the strut region to be treated as the only cause. The Commission's finding was broader than that, but they show why investigators paid attention to local geometry and local loading, not just to the joint as a complete circle. A circular joint can fail locally. That is part of the lesson here. The field joint wrapped around the motor, but the conditions around that circumference were not identical in every practical sense. The metal parts had manufacturing dimensions. They had been assembled and processed. The motor had flight history and reuse considerations. The materials had their own behavior. And then, at ignition, loads entered the structure in ways that could make one part of the joint more demanding than another. For the O-ring, the demand was simple to state and difficult to guarantee. It had to remain capable of sealing while the joint opened. It had to respond faster than the gas path developed. It had to do that in the presence of putty, pressure changes, possible debris, and the motion of the hardware around it. The secondary O-ring existed as another seal, but the system still depended on the field joint behaving within limits that allowed sealing to occur. If the primary seal was delayed and the joint geometry changed too much, the protective sequence could be compromised before backup protection could be relied upon. This is why the warning signs were not only scorch marks or erosion found after earlier flights. The warning signs were also built into the sensitivity of the design itself. The joint's performance depended on tolerances, temperature, rubber response, assembly condition, and launch loads all aligning closely enough. A successful previous flight did not prove that the joint had generous margin. It could also mean that, on that flight, the combination of conditions had not crossed the line. The Rogers Commission's finding forces the story away from a simple broken part and toward a system that had become too dependent on favorable circumstances. The aft field joint had to seal instantly, but it was asked to do so while its own shape was changing. The tang and clevis gap was not just a measurement, it was the space the seal had to defeat. Gap opening during ignition was not just movement, it was a race between metal deformation and rubber recovery. The 310-degree strut region was not just a coordinate, it was a place where local loading could make that race harder. And one sensitivity was about to dominate the launch decision more than any other. If the O-ring had to move quickly, then anything that slowed rubber recovery mattered. If the joint opened at ignition, then anything that made the seal sluggish mattered. On the morning of January 28, 1986, the most visible condition at Kennedy Space Center was cold. For the field joint, cold was not just weather. It was a mechanical change in the material that had to close the gap before fire could pass through. Cold mattered because the joint was already a race. The metal parts could move under ignition loads, the gap could open, and the O-ring had to recover quickly enough to stay in contact with the sealing surfaces. In warmer conditions, that recovery was part of the design expectation. In cold conditions, the same rubber did not behave the same way. This was not simply a question of comfort at Kennedy Space Center, or of whether ice on the launch structure looked unusual in Florida. It was a question of material behavior. The O-rings in the solid rocket motor field joints were rubber seals. Their job depended on resiliency, the ability to be squeezed, displaced, and then returned toward shape fast enough to block the path of hot combustion gas. If that return was delayed, even for a short interval, the timing of the seal changed. And in the first moments after ignition, timing was everything. NASA's later accident material and the Rogers Commission both identified the cold weather before launch as a central aggravating condition. The Commission's finding was mechanical and direct. Cold O-rings lost resiliency. Rubber that might respond quickly at a higher temperature became slower and stiffer as the temperature dropped. The seal still looked like an O-ring. It was still installed in the joint O, but its ability to perform during the ignition transient was reduced. The Commission gave one comparison that made the problem plain. A compressed O-ring at 75 degrees Fahrenheit returned to shape about 5 times faster than a compressed O-ring at 30 degrees Fahrenheit. That was not a small difference. It meant that the same part, with the same basic function, could respond on a very different timescale, depending on temperature. In a joint where the gap could open rapidly at ignition, a seal that recovered 5 times more slowly was not merely less efficient. It was less able to keep up. The warning was especially important because the O-ring did not seal in isolation. It was part of a system involving the tang and clevis, the zinc chromate putty, the primary and secondary O-rings, the pressure inside the motor, and the movement of the joint as the booster came alive. The O-ring could be helped by pressure actuation, but pressure actuation also required conditions that allowed the seal to move into place. If cold made the rubber slower to respond, then the pressure that was supposed to help seal the joint could also arrive during the period when the joint geometry was changing and the seal had not yet fully followed. That is why the weather forecast on the night before launch was not a side issue. It reached directly into the mechanism. The concern raised during the January 27, 1986 meetings and teleconferences between Morton Thiokol engineers and NASA personnel was not simply that the morning would be cold. It was that the forecast temperatures at Kennedy Space Center were far below the previous flight experience base for O-ring temperature. That phrase, flight experience base, was important. The shuttle program had already flown many missions, and those flights had created a practical record of conditions under which the solid rocket motor joints had been used. Engineers could look at earlier launches and ask what temperatures the O-rings had seen, and what damage, erosion, blow-by, or soot had appeared afterward. The night before Challenger's launch, the concern was that the forecast would take the joint into colder territory than the data supported. Morton Thiokol's initial engineering recommendation that night was not to launch below the prior O-ring temperature experience base of 53 degrees Fahrenheit. That recommendation tied the weather to the known record. It did not claim that the O-rings would automatically fail below that point. It said that the available flight experience did not support launching below it. The number mattered because it marked the boundary between what had been flown and what was now being proposed. In an engineering culture, experience can become a form of evidence. Not perfect evidence, and not the same as proof of safety, but evidence nonetheless. If a component has survived within a certain range, managers may be tempted to treat that range as acceptable. But when conditions move outside that range, the argument changes. The question is no longer just whether a part has worked before. It becomes whether there is a solid reason to believe it will work under conditions it has not previously demonstrated. For the O-rings, the cold forecast sharpened every existing concern. A joint already known to be sensitive to temperature was being asked to operate in a temperature range below the record that engineers had to point to. A seal already dependent on rapid recovery was being asked to recover in conditions known to slow it. A mechanism already vulnerable to gap opening was being placed in a morning when rubber resiliency was degraded. The severe cold wave at Kennedy Space Center made the condition visible. Ice appeared at the launch site. Florida, usually part of the shuttle program's image of clear coastal launch weather, was under a cold that seemed out of place. But the visible ice was only the surface sign. The deeper issue was hidden inside the right solid rocket booster aft field joint, where the O-rings had no way to explain that their material properties had changed. Rubber does not need to crack or break apart to become less capable. It can simply become slower. It can resist deformation differently. It can recover less readily after being compressed. In a household object, that kind of change might be an annoyance. In a rocket motor field joint, it could decide whether hot gas stayed inside the case or found a route past the seal. The Rogers Commission's comparison between 75 degrees Fahrenheit and 30 degrees Fahrenheit gave investigators and the public a way to understand this difference. The problem was not mysterious. It was not an exotic failure mode that appeared from nowhere. It was a known characteristic of a material being used in a demanding mechanical environment. The O-ring's job was dynamic. It had to respond when the joint moved, when pressure rose, and when the combustion process began. Cold made that response slower. This is why temperature could not be separated from the earlier discussion of geometry. If the joint had been perfectly rigid, rubber response time might have mattered differently. If the seal had not needed to follow opening gaps, its resiliency might have been less critical. But the field joint was sensitive to dynamic loading and local gap opening. The O-ring was part of a moving system. Cold reduced the ability of the seal to move with it. On the night before launch, that mechanical fact became a decision problem. Engineers at Morton Thiokol's Wasatch plant in Utah and NASA personnel connected to the launch decision had to evaluate a cold weather launch from Kennedy Space Center. The concern was not abstract. The prior flight experience base was being exceeded on the low temperature side. The O-ring resiliency data pointed in the same direction. The Commission would later describe the launch decision as flawed and based on incomplete and sometimes misleading information, but even before that judgment, the technical issue was clear enough to be argued. Colder rubber sealed more slowly, and this launch was expected to be colder than the record that had been used before. The tragedy of this part of the story is that cold did not introduce a brand new weakness. It amplified a known one. The O-ring problem already existed in the joint design, in its sensitivity, in the way it depended on fast sealing during ignition. Cold took that vulnerability and made it more severe at the exact moment when the seal needed to be most responsive. And the concern about cold did not stand alone. It was attached to a history. Before STS-51L, earlier shuttle flights had already come back with marks that engineers could read: erosion, blow-by, soot, evidence that hot gas had challenged the seals. Those flights had survived, but they had not been silent. The cold forecast in January 1986 mattered because it met a record that already contained warnings. The rubber was about to be tested below its previous experience base, and the joint had already shown that, under less extreme conditions, it could leave evidence of distress. The cold forecast in January 1986 mattered because it did not arrive into an empty record. It arrived into a program that had already seen the solid rocket motor seals come back with signs of distress. The marks were not dramatic to the public. They were not visible from the grandstands at Kennedy Space Center. They were found after flight, in hardware inspections, in engineering reviews, in the careful reading of soot, erosion, and heat damage around parts that were supposed to keep combustion gas contained. That distinction is important. Before Challenger's final launch, the O-ring problem was not only a fear about what might happen someday. Earlier shuttle flights had already shown that hot gas could move into places it was not supposed to go. The system had flown and survived, but survival had begun to blur the meaning of the evidence. Each safe landing could be read as proof that the design had margin. The damaged seals suggested something more troubling. The margin was being used. In the field joint, the primary O-ring was intended to seal against the combustion pressure inside the solid rocket motor. Behind it sat the secondary O-ring, a backup in name and position. But the Rogers Commission later emphasized that the joint design was sensitive to several conditions at once: temperature, material behavior, dimensions, processing, reuse, and dynamic loading. When earlier flights showed O-ring erosion, blow-by, or soot, those marks were not isolated blemishes. They were evidence that the joint was operating in a narrow and uncertain space. Engineers had names for what they were seeing. Blow-by meant hot gas had passed the primary sealing area before the seal fully stopped it. Erosion meant the O-ring material had been eaten away by heat and combustion products. Soot meant combustion gas had reached surfaces beyond where it should have remained. None of these findings by itself automatically meant a vehicle would fail on the next flight. But together, they showed that the seal system was not behaving as cleanly as the design required. The warning history became especially serious in January 1985, 1 year before STS-51L. That month, the shuttle mission STS-51C flew. Afterward, inspection of the solid rocket motor hardware produced significant concern about the O-rings. The flight had returned safely, but the recovered evidence showed that the sealing system had been challenged. For engineers looking at field joint behavior, this was not a theoretical note in a design manual. It was flight hardware marked by real combustion conditions. STS-51C mattered because it helped shift the conversation. The question was no longer simply whether the field joint might be sensitive under certain conditions. The question became why a flown joint had shown damage, and whether the same mechanism could appear again. Once a reusable launch system accumulates flight history, that history becomes part of its safety case. Good history can build confidence. Damaged history should narrow it. The shuttle program was built around repetition. Boosters were recovered from the ocean, inspected, refurbished, and used again. The solid rocket motor contractor, Morton Thiokol, and NASA centers such as Marshall Space Flight Center had to convert flight evidence into engineering judgment. Each returned segment could be studied for signs of how the joint had behaved during ignition and ascent. In that process, the O-ring marks became records of brief events that no camera could see directly inside the joint. Then came STS-51B in April 1985. After that flight, concerns became strong enough that the issue moved further into formal management attention. The earlier evidence had already shown erosion and blow-by in the system. STS-51B added to the pattern. It reinforced the possibility that the field joint seals could be damaged during flight, even when the vehicle completed its mission. This is one of the most difficult parts of the Challenger story, because the evidence carried two meanings at once. On one hand, the flights had succeeded. The boosters had not destroyed the vehicle. The O-rings, though damaged, had not led to catastrophe. On the other hand, the very fact of damage showed that the first line of defense had sometimes been compromised. A seal that survives after being eroded is not the same as a seal that was never threatened. A joint that contains pressure after blow-by is not the same as a joint that's sealed instantly and cleanly. In a hazardous system, successful outcomes can conceal weakening assumptions. If a component performs imperfectly and the mission still succeeds, managers may come to treat the imperfection as acceptable experience. Engineers may see the same evidence differently. To them, erosion and soot can mean that a failure path has already begun to appear, even if it has not yet completed itself. The flight did not fail, but the hardware came back saying that the design had been tested in an unintended way. The Rogers Commission later described the accident as the failure of the pressure seal in the aft field joint of the right solid rocket motor. That finding gave the earlier flight history a sharper meaning. The same class of hardware that failed on STS-51L had already produced warning signs on previous missions. The record did not need to predict every detail of the final accident to be relevant. It only needed to show that combustion gas had, before, challenged the O-ring sealing system. The evidence after STS-51C and STS-51B was especially important because it connected engineering concern to actual operations. Temperature sensitivity, joint rotation, O-ring resiliency, and pressure actuation could all be discussed as mechanisms. But damaged O-rings turned mechanisms into experience. They showed that the joint could fail to seal immediately enough to avoid heating and erosion. They showed that hot gases and combustion debris could reach the sealing material. And they showed that the backup assumptions around the primary and secondary O-rings deserved far more caution than routine flight success might suggest. At Morton Thiokol's Wasatch plant in Utah, engineers were close to the hardware and to the details of the seal behavior. At Marshall Space Flight Center in Huntsville, Alabama, NASA managers were responsible for the Solid Rocket Booster project. Between contractor and agency, the O-ring issue became a continuing subject of discussion. It was not a mystery hidden from everyone until the night before launch. It was known in pieces, argued over in reviews, and carried forward through the program as flights continued. But programs do not respond only to evidence. They respond to how evidence is classified. If a finding is treated as an anomaly that has been bounded, flight can continue. If it is treated as proof of a critical and unresolved failure mode, the pressure to stop and redesign becomes stronger. The marks on the earlier boosters forced that classification problem. Were these signs of acceptable erosion within experience, or signs that the joint had already come too close to losing its seal? The answer became increasingly consequential as the shuttle schedule moved through 1985. By then, the solid rocket motor field joint had a documented history. The O-ring issue had passed beyond speculation. There had been flights with erosion. There had been blow-by. There had been soot. The system had not failed catastrophically, but the evidence showed that it had not performed with the clean redundancy implied by its design. This history also shaped the meaning of the cold weather concern before STS-51L. The launch night debate was not simply about whether rubber becomes stiffer in cold conditions. It was about cold rubber in a joint that already had a record of distress. If prior flights under warmer conditions had produced O-ring damage, then a forecast below the previous flight experience base was not just an unfamiliar condition. It was an unfamiliar condition applied to a known vulnerability. The earlier flights left marks, and those marks left obligations. They required explanation. They required corrective action. They required honest communication up the chain of decision-making. After STS-51B, the concern was serious enough to become tied to a formal launch constraint for later flights, including STS-51F and those that followed. That step showed that the O-ring issue had entered a more official category of risk. Yet the way that constraint was handled would become its own warning sign, because a documented hazard can still be normalized if each launch is allowed to proceed around it. The earlier flights left obligations, and one of those obligations took a formal shape after STS-51B. The O-ring damage was no longer just an engineering concern moving through reports and post-flight inspections. It became tied to a launch constraint, a procedural signal that a condition existed which could affect flight safety unless it was resolved, accepted, or waived. That distinction matters. In a program as large as the Space Shuttle, risk could not be carried only in memory. It had to be carried in documents, review processes, signatures, and briefings. A launch constraint was one way of saying that a known problem had not simply disappeared because the last mission survived. It was a way of holding the system's attention. After STS-51B, that attention was directed at the solid rocket booster field joint seals. The flight had added to a record that already included O-ring erosion, blow-by, and soot on earlier missions. The joint was supposed to prevent hot combustion gases from escaping the solid rocket motor, but flight hardware had returned with evidence that the seal system had been challenged. The concern was serious enough that a launch constraint was placed on STS-51F and subsequent flights. That phrase, subsequent flights, is important. The constraint did not apply to one isolated mission, and it did not disappear before Challenger's final launch. It remained part of the record for later shuttle flights, including STS-51L. In theory, a launch constraint should have forced a clear question before each flight. Has the problem been corrected, or is the program knowingly accepting the risk? In practice, the Rogers Commission found something more troubling. The constraint was repeatedly waived by Lawrence B. Malloy, the Marshall Solid Rocket Booster project manager. Marshall Space Flight Center in Huntsville, Alabama, carried central responsibility for the Solid Rocket Booster project. Morton Thiokol, with major engineering work at the Wasatch plant in Utah, was the contractor for the solid rocket motor. The hardware flew from Kennedy Space Center in Florida, but important technical authority and management responsibility flowed through Marshall. Within that structure, Malloy was not a distant observer. He was a key NASA manager in the booster chain. The waivers did not mean that every person involved believed the joint was safe in an absolute sense. A waiver means something more specific and more dangerous. A known condition is allowed to remain unresolved for the purpose of proceeding. It is an administrative act, but it has a physical consequence. The metal joint still rotates under ignition loads. The O-rings still have to seal. Hot gas still searches for a path. Paper does not change the behavior of rubber. That is why the repeated waivers became one of the central organizational warning signs before STS-51L. The O-ring issue had already moved from post-flight observation into formal constraint. Yet the shuttle program continued to launch. In a technical organization, repetition can change the feel of danger. The first instance of erosion may trigger alarm. The next may trigger analysis. A later one may be described in relation to the earlier ones. Worse than, less than, comparable to. Over time, if flights continue to succeed, the survival of the previous mission can begin to compete with the evidence of damage. The hardware becomes not safe, but familiar. The risk becomes not solved, but accustomed. The Rogers Commission's work after the accident showed how deeply that pattern mattered. The Commission did not treat the Challenger disaster as only a failed part. It examined the decision system that allowed the part to remain in service, flight after flight, without the full meaning of the evidence reaching the people who needed to hear it. One of the Commission's findings was especially stark. Level 1 and Level 2 NASA officials were not told about the launch constraint, the reasons behind it, or the series of waivers before STS-51L. This was not a minor communication gap. Level 1 and Level 2 were the higher layers of NASA's shuttle management structure. Those officials were responsible for major program decisions, and their understanding of risk depended on what was elevated to them. If the launch constraint remained lower in the system, then the senior decision-makers could not weigh its meaning fully. They could not ask why the constraint existed. They could not ask what had changed since it was imposed. They could not ask how many times it had been waived. They could not compare the formal history of the O-ring problem against the conditions expected for the upcoming launch. The problem, then, was not only that a constraint existed, it was that the constraint had become separated from the broader decision process. A warning was present in the system, but it did not travel with enough force. This separation is one of the quiet lessons of the Challenger record. Large institutions often depend on layered review because no single person can hold every detail. But layered review only works if the significant details are passed upward clearly. A technical concern becomes a management concern when it carries flight safety implications. A launch constraint should have been one of the signs that the O-ring problem had crossed that line. Instead, according to the Rogers Commission, senior NASA officials were not told the full story. They were not told that the constraint had been placed after STS-51B. They were not told the reasons behind it. They were not told that the constraint had been waived again and again. That missing context changed the meaning of later discussions. A manager hearing about an O-ring issue without the history of a launch constraint might hear a technical problem under study. A manager hearing the same issue with the history of repeated waivers would hear something different,
a known safety concern that had been accepted repeatedly without final resolution.
The facts are not the same when the history is removed. By the time STS-51L moved toward launch, the shuttle program had already accumulated several kinds of warning. There were physical warnings in recovered hardware, erosion, blow-by, soot. There were analytical warnings in engineering discussions about field joint behavior, pressure actuation, and O-ring resiliency. There were environmental warnings as forecasts pointed toward unusually cold temperatures at Kennedy Space Center. And there was a procedural warning in the launch constraint itself. The constraint should have helped preserve institutional memory. It should have prevented each flight from being treated as a fresh start. It should have connected STS-51L back to STS-51B and the flights before it. But the Commission's finding shows that the record was not functioning that way at the highest levels. There is a harsh simplicity in that. A warning can exist and still fail. It can be written down and still not be understood by the right people. It can be serious enough to require a waiver and still become routine through repetition. The failure is not only in the absence of information. Sometimes it is in the management of information that already exists. For the engineers closest to the seals, the problem had not gone away. The launch constraint did not repair the field joint. The waivers did not explain the erosion. The prior flights did not prove safety. They proved that the system had survived while showing signs of distress. At Morton Thiokol, some engineers continued to see the O-ring issue as urgent, unresolved, and potentially catastrophic. One of those engineers was Roger Boisjoly. By the summer of 1985, months before Challenger's final launch, he would put his concern into a direct internal warning. The title itself would name the hazard plainly: SRM O-ring erosion / potential failure criticality. In that memo, the issue that had been waived in launch paperwork would appear in a different form as an engineer's alarm about what could happen if the field joint seal problem was not treated with the priority it demanded. By the summer of 1985, the field joint problem had moved through several forms. It had appeared as physical evidence on recovered hardware. It had appeared as discussion inside NASA and Morton Thiokol. It had appeared as a launch constraint that could be waived. But for Roger Boisjoly, an engineer at Morton Thiokol, the problem demanded a more direct warning. On July 31, 1985, Boisjoly wrote an internal memorandum titled SRM O-ring erosion / potential failure criticality. The title was technical, but not vague. It named a part of the system at issue, the solid rocket motor O-rings. It named the damage pattern, erosion. And it named the consequence that mattered most in flight safety work, potential failure criticality. This was not a public document. It was not part of a press briefing, and it was not written for the audience that watched shuttle launches from schoolrooms, living rooms, or the beaches near Cape Canaveral. It belonged to the engineering record inside Morton Thiokol, the company responsible for the shuttle's solid rocket motors, with major engineering work at the Wasatch plant in Utah. But the warning it contained reached beyond ordinary paperwork. Boisjoly was not simply reporting that a component needed improvement. He was warning that if the field joint O-ring problem was not treated with the priority it required, the result could be the loss of a flight and launch pad facilities. In the language of engineering risk, that was a grave statement. The shuttle's solid rocket motors were not minor accessories to the vehicle. They provided enormous thrust during the first part of ascent, and once ignited, they could not be shut down. Their field joints had to contain hot combustion gases under violent conditions. The tang and clevis metal parts, zinc chromate putty, and the 2 rubber O-rings were all part of a system meant to keep those gases inside the motor. If that seal system failed, the consequences would not be limited to a maintenance issue after landing. There would be no landing. What made Boisjoly's memo so important was its connection to a known, specific mechanism. It was not a generalized concern about quality, or a broad unease about schedule, or a vague sense that the shuttle was becoming too routine. It was an alarm attached to the same basic joint system that the Rogers Commission would later identify as central to the Challenger accident. After the disaster, the Commission concluded that the immediate cause was failure of the pressure seal in the aft field joint of the right solid rocket motor. Boisjoly's memo, written nearly 6 months before the launch of STS-51L, had already focused attention on the erosion and failure potential of those seals. The timing matters. July 31st came after earlier flights had shown that O-ring damage was not merely theoretical. STS-51C in January 1985 and STS-51B in April 1985 had produced significant concern. Post-flight evidence had shown erosion, blow-by, or soot on earlier missions. These marks meant that hot gas had challenged the seal system and in some cases had gotten past where it was expected to be stopped. The motors had not failed on those flights, but their survival could be misleading. A system can survive a near miss and still be warning its operators. Boisjoly understood that distinction. The fact that previous launches had succeeded did not erase the evidence of damage. In the field joint system, the O-rings were supposed to seal quickly during ignition. At the same moment, the joint could rotate and the gap between the tang and clevis could open. If the primary O-ring did not respond in time, hot gas could move through the joint and erode the rubber. If erosion became severe enough, or if the sealing sequence failed under the wrong conditions, the backup provided by the secondary O-ring might not be enough. The details were mechanical, but the risk was simple. The pressure boundary of a rocket motor could be lost. That is why the memo's warning about losing a flight and launch pad facilities was so concrete. It placed the O-ring issue in the category of catastrophic failure, not routine wear. It said, in effect, that the damage seen in earlier motors should not be normalized just because the flights had returned no crew fatalities and no destroyed vehicle. The evidence should have forced attention forward, toward corrective action, not backward, toward reassurance. There is a quiet tension in this part of the record. NASA's shuttle program depended on repeated flight. The boosters were part of a system that was meant to support an operational schedule, with missions following one another through an ambitious calendar. Morton Thiokol, Marshall Space Flight Center, Kennedy Space Center, Johnson Space Center, and NASA headquarters all existed within a chain of responsibility in which technical concerns had to move upward clearly and accurately. But a warning can lose force if it remains inside a compartment. It can also lose force if it is treated as one more item among many, especially when launches continue and no catastrophe has yet occurred. The July memo shows that at least one engineer was trying to prevent that loss of force. Boisjoly's concern was not merely that O-rings had eroded. It was that the erosion problem needed priority. In safety engineering, priority is not an administrative detail. It determines whether people, money, testing, redesign work, and management attention are directed toward a hazard before the hazard becomes an accident. If a problem is understood as critical but not treated as urgent, the organization may continue to record it without truly acting on it. The Rogers Commission would later describe the solid rocket motor field joint design as unacceptably sensitive to several factors, including temperature, physical dimensions, material behavior, reuse, processing, and dynamic loading. Boisjoly's memo did not need to predict every detail of the STS-51L launch conditions to be significant. Its importance lies in the way it identified the field joint O-ring erosion problem as a possible path to disaster. The later cold weather at Kennedy Space Center would add another dangerous factor, because cold O-rings lost resiliency and could be slower to seal. But months before that freezing launch morning, the joint system had already been singled out internally as a critical danger. The memo also reminds us that warning signs in complex systems are often written in ordinary forms. A memorandum can look calm. It can be filed, copied, discussed, or deferred. It may not carry the visual force of smoke on launch video or flame from a booster joint. But in the history of Challenger, Boisjoly's July 31st memo stands as one of the clearest written alarms before the disaster. It named the component. It described the damage. It connected the technical issue to the possibility of losing a flight. That connection is what gives the document its weight. It stripped away the comfort of abstraction. O-ring erosion was not only a matter of seal performance, it was a threat to the vehicle and the pad. The field joint was not just an engineering subsystem, it was part of the pressure boundary holding back the combustion gases of a solid rocket motor. The earlier marks on recovered hardware were not merely historical data, they were evidence of a recurring condition that demanded action. And yet the problem remained unresolved. The launch constraint had not solved it. The waivers had not solved it. The memo itself, however direct, did not make the risk disappear. Inside Morton Thiokol,
Concern continued through the late summer and into the fall of 1985. Other engineers would also press for attention to the seal problem, and the language in the internal record would grow even more urgent. By October 1st, Robert Ebeling would produce a report that captured the frustration of engineers who believed the SEAL task force was delayed and undersupported. One word in that report would carry the tone of a distress call: help. By the fall of 1985, the warning no longer belonged to one memo, one inspection, or one engineer. Roger Boisjoly's July warning had given the field joint problem a sharp, written form. But inside Morton Thiokol, at the Wasatch plant in Utah, the concern was broader than a single document. The engineers working close to the solid rocket motor seals were not looking at an abstract design disagreement. They were looking at a system that had already shown erosion, blow-by, and soot on earlier flights, and they were trying to get the problem treated with the urgency they believed it required. On October 1st, 1985, another Thiokol engineer, Robert Ebeling, put that frustration into writing. The report is remembered in part because of one word. Ebeling used the word help in describing delays and lack of support for the SEAL task force. It was not the technical language of a finished engineering solution. It was the language of a group that believed it was not getting what it needed. In a record filled with terms like tang, clevis, primary O-ring, secondary O-ring, pressure actuation, and joint rotation, the word stood out because it was so plain. It suggested not only that a problem existed, but that the people assigned to work on it felt constrained by time, resources, or organizational attention. That distinction matters. A technical problem can be acknowledged in many ways without being solved. It can be discussed in meetings. It can be described in reports. It can be attached to a launch constraint. It can be reviewed after a flight and then carried forward into the next mission. But Ebeling's October report pointed to something deeper: the concern that the SEAL task force itself was delayed and undersupported. The SEAL task force existed because the O-ring issue had become too visible to ignore. The solid rocket motor field joint had to perform under extreme conditions, and it had to perform immediately. During ignition, the joint was subjected to pressure and motion. The tang to clevis gap could open. The O-rings had to respond quickly enough to seal before hot combustion gases found a path through the joint. Previous flights had already shown that the system was not behaving as cleanly as intended. Erosion and blow-by were not theoretical possibilities. They had been seen in recovered hardware. At the Wasatch plant, this was not a public story. It was internal engineering work, moving through memos, task force activity, and contractor communication with NASA's Marshall Space Flight Center. Morton Thiokol built the solid rocket motors. Marshall managed the solid rocket booster project. The relationship required trust, but it also required clarity, especially when a component in the pressure boundary showed signs of distress. By October, the field joint seal issue was already living in several places at once. It was in the hardware record from flights such as STS-51C and STS-51B. It was in Boisjoly's July 31st memo, which warned that failure to prioritize the O-ring problem could risk losing a flight and launch pad facilities. It was in the launch constraint that had been placed on later flights and then repeatedly waived. And it was now in Ebeling's report, where the word help captured the sense that the task force had not been given enough support to move quickly. The danger in this kind of situation is that documentation can create the appearance of control. A problem that has been written down may seem managed. A task force may suggest progress. A waiver may suggest that risk has been formally considered. But the Rogers Commission would later describe a pattern in which the field joint design was unacceptably sensitive to temperature, physical dimensions, material behavior, reuse, processing, and dynamic loading. Those sensitivities were not small administrative matters. They were part of the mechanical chain that could determine whether the joint sealed or leaked in the first moments after ignition. Ebeling's report belongs in that chain because it shows the human and organizational side of the technical warning. Engineers were not only identifying the seal problem, some were also worried about the pace and support of the response. The word help did not calculate erosion depth. It did not measure O-ring resiliency. It did not model local joint gap opening. But it told management that the people assigned to the issue believed the process around the issue was failing them. That is why the report is more than a footnote. It helps show that months before Challenger's final launch, The seal issue was not merely a debated detail in a complex machine. It had become a sustained engineering concern at the contractor responsible for the motors. At Morton Thiacol's Wasatch plant, engineers were looking at evidence from past flights and trying to push the organization toward a stronger response. The field joint was unforgiving because its failure mode could be fast. If hot gases passed the primary seal, they could damage the O-ring. If the secondary O-ring did not seal in time, the joint could become a path for combustion gases escaping the motor. The system depended on geometry, materials, timing, and temperature all lining up under violent conditions. The earlier flight evidence had already raised questions about whether the joint provided the safety margin that had been assumed. Ebeling's October report also shows how warnings can accumulate without producing decisive action. A warning does not have to be ignored completely to be ineffective. It can be received, filed, discussed, partially acted upon, and still fail to change the decision environment. The problem can become familiar. Managers can grow accustomed to seeing damage that did not lead to catastrophe on previous flights. Engineers can continue to object, but their objections may become one voice among many demands: schedule, hardware flow, mission planning, and the pressure to keep a national launch program moving. The Rogers Commission later found that senior Level 1 and Level 2 NASA officials were not told about the launch constraint, the reasons behind it, or the series of waivers before STS-51L. That finding belongs to the larger communication failure. But Ebeling's report gives the failure an earlier internal texture. It shows that within the contractor's own engineering world, the seal problem had not settled into confidence. It remained urgent enough for a written plea. The word help is powerful because it is not dramatic in the usual sense. It is not a prediction delivered after the fact. It is a trace from inside the process, written before the disaster, when there was still time for a different level of attention. It reflects the frustration of engineers trying to work a known problem before it became irreversible. By October 1st, 1985, Challenger's final flight was still months away. The cold morning at Kennedy Space Center had not arrived. The launch night teleconference had not happened. The final reversal of Morton Thiacol's initial no-launch recommendation was still in the future. But the record already contained a pattern: damage on earlier flights, a formal constraint that could be waived, Boisjoly's direct warning, and Ebeling's plea for help. Together, those signs make the seal issue look less like a hidden defect and more like a known, unresolved hazard moving through an organization that had not yet found the will, the resources, or the communication discipline to stop and fix it. The engineers at Wasatch were not outside the system. They were part of the system. Their reports were internal signals from the people closest to the motor's vulnerable joint. And while those signals continued, NASA was preparing for an unusually ambitious year. The shuttle program was not standing still while the O-ring debate continued. Missions were being planned, payloads assigned, launch sites prepared, and schedules arranged around a program that expected to fly often. The unresolved seal problem would soon have to exist inside that larger tempo, where technical risk and institutional momentum were being managed at the same time. The unresolved seal problem was not moving through an empty calendar. It was moving through a shuttle program that expected to be busy, visible, and operational in a way no earlier space program had been. By late 1985 and early 1986, NASA was preparing for an unusually ambitious shuttle year. The plan called for as many as 15 missions, a pace that would have tested not only orbiters, boosters, launch pads, and payload teams, but also the management systems that decided when a technical concern was serious enough to slow the flow. That context matters, but it must be handled carefully. The Challenger accident cannot be reduced to one phrase, such as schedule pressure. The Rogers Commission identified a physical failure in the aft field joint of the right solid rocket motor, and it also examined the flawed decision process that allowed launch to proceed. The record does not need a single, simple cause. It shows something more complicated: a technical hazard already known inside NASA and Morton Thiacol, managed through constraints and waivers, existing within a program that was trying to fly often and demonstrate that the shuttle had become a reliable national transportation system. The shuttle had always carried that promise. It was not only a spacecraft. It was meant to be a reusable system, one that could carry satellites, scientific instruments, classified payloads, commercial hardware, and people with a frequency unlike the earlier era of rockets used once and discarded. By 1986, that promise was being translated into a crowded manifest. Flights were not just missions in isolation.
They were links in a chain.
A delay in one place could affect another payload, another crew, another launch window, another center, another customer. STS-51L was part of that chain. Challenger's flight was planned as the 25th mission of the Space Shuttle program and the orbiter's 10th flight. Its payloads included TDRS-B, a tracking and data relay satellite, and the Spartan Halley astronomy satellite intended to observe Halley's comet. The mission also carried the Teacher in Space program into the public eye, with S. Krista McAuliffe scheduled to conduct live lessons from orbit. To viewers outside NASA, this made the mission feel especially human and immediate. Inside the agency, it was also one mission among many in a year designed to prove a high operational tempo. The planned year extended beyond Kennedy Space Center. One of the major goals for 1986 was the first West Coast shuttle launch from Vandenberg Air Force Base in California. That launch would have marked an expansion of shuttle operations beyond Florida, adding a new geographic and institutional dimension to the program. Vandenberg represented more than a second launch site. It represented the idea that the shuttle system could support a broader national launch capability, with different routes to orbit and a wider range of mission requirements. At the same time, NASA was preparing for later major science missions. The shuttle was being positioned as a platform for national priorities that ranged from communications to astronomy. Each mission had its own technical requirements, payload teams, and planning history. Each one depended on the broader system remaining in motion. In that environment, a launch date was never merely a date. It was a point where engineering, operations, public commitments, and institutional expectations came together. This is the organizational atmosphere in which the O-ring issue was being handled. The concern was not unknown. Earlier flights had shown O-ring erosion, blow-by, or soot. After STS-51B, a launch constraint had been placed on STS-51F and subsequent flights, including STS-51L. That constraint signaled that the field joint seal problem had flight safety importance. But the constraint was repeatedly waived by Lawrence B. Malloy, the Marshall Solid Rocket Booster Project Manager. A waiver can sound administrative, almost routine. In a large technical organization, waivers are part of how work proceeds when a known issue has not yet been fully closed. They do not automatically mean carelessness. They can reflect a judgment that a system is acceptable for flight under specified conditions. But that is precisely why communication matters. A waiver depends on the quality of the information behind it, the clarity of the risk being accepted, and the level of leadership that understands what is being carried forward. The Rogers Commission found that Level 1 and Level 2 NASA officials were not told about the launch constraint, the reasons behind it, or the series of waivers before STS-51L. That finding is central to understanding the management environment. The issue was not only whether engineers knew of O-ring erosion. Some did. It was not only whether managers had seen pieces of the problem. Some had. The deeper question was whether the organization's highest decision levels had a complete and accurate picture of the hazard that was being normalized flight by flight. The ambitious shuttle year made that question more important, not less. When a program expects to fly many times, a recurring anomaly can begin to look familiar. The absence of catastrophe on previous flights can be mistaken for evidence of safety. If an O-ring had eroded before and the mission survived, the survival could become part of the rationale for continuing, even though the erosion itself showed that the joint was not behaving as intended. In a busy manifest, that kind of normalization can become quiet. It does not require a dramatic order. It can happen through reviews, paperwork, repeated acceptance, and the steady pressure to keep preparing the next vehicle. The shuttle program also involved several centers with different responsibilities. Kennedy Space Center in Florida handled launch processing. Marshall Space Flight Center in Huntsville, Alabama, carried responsibility for the solid rocket boosters. Johnson Space Center in Houston, Texas, was deeply tied to crew and mission operations. NASA headquarters sat above the program structure. Morton Thiokol, with major engineering work at the Wasatch plant in Utah, built the solid rocket motors. The O-ring concern had to move through this network. It had to be described, understood, elevated, and acted upon across institutional boundaries. That was not easy, even in a calm year. In an unusually ambitious year, it became still more demanding. Technical concerns had to compete for attention with flight readiness reviews, payload schedules, weather conditions, vehicle processing, and inter-center coordination. The more complex the system, the more dangerous incomplete communication could become. A warning held at one level, softened at another, or translated into a waiver without full explanation, could lose its force before reaching the people who might have stopped a launch. By January 1986, Challenger's mission sat at the front edge of this broader plan. The flight had already attracted public attention because of the Teacher in Space program. It carried operational payloads and scientific objectives. It also stood within a year in which NASA intended to increase the shuttle's tempo and demonstrate its reach, including the planned move toward a first launch from Vandenberg Air Force Base. The agency was not simply preparing one launch. It was managing a full program identity, frequent, capable, national, and visible. None of that changed the physics of the right solid rocket motor field joint. The tang and clevis still had to hold their geometry. The zinc chromate putty and the two rubber O-rings still had to prevent hot combustion gases from escaping. The primary O-ring still had to respond quickly enough during ignition. Cold rubber still lost resiliency. A known seal concern did not become less serious because the calendar was full. But the calendar helps explain the world in which the final decision was made. The O-ring problem had already produced physical evidence, internal memoranda, requests for help, a launch constraint, and repeated waivers. Now it was being carried into a launch campaign during a year that expected the shuttle system to perform at a high pace. The question was not whether NASA had ambition. It clearly did. The question was whether the machinery of decision-making could slow itself when the technical evidence required it. On January 27, 1986, that question became immediate. The concern would no longer be an abstract entry in a history of erosion or a memo from months earlier. It would be tied to a specific forecast, a specific launch pad, a specific right and left booster, and temperatures far below the previous O-ring flight experience base. Engineers from Morton Thiokol and personnel from NASA would enter a series of meetings and teleconferences in which the unresolved seal problem, the cold Florida night, and the momentum of the shuttle program all converged. The forecast now gave the unresolved seal problem a deadline. For months, the concern had lived in inspection records, internal memoranda, task force discussions, and launch constraints. On January 27, 1986, it became a question that had to be answered before morning. Could the solid rocket motors be launched safely in temperatures far colder than the O-rings had experienced in flight? At Kennedy Space Center, Challenger stood at Launch Complex 39B. The mission was STS-51L, and the countdown had already been delayed before. But the issue that came forward on the night before launch was not simply delay. It was temperature, and temperature meant something specific to the field joint. The rubber O-rings in the booster joints had to respond quickly during ignition. They had to seal while the metal joint was moving, while pressure was rising, and while the gap between tang and clevis could open under load. If the rubber was cold and slow, the margin that had already concerned engineers could become smaller still. The weather expected at Kennedy Space Center was outside the experience base that mattered most to Morton Thiokol's engineers. Earlier shuttle flights had launched with O-ring temperatures no lower than 53 degrees Fahrenheit. That number did not represent a fully proven safe boundary. It represented the lowest previous flight experience. Below it, the data were thinner, the predictions less certain, and the earlier evidence of erosion and blow-by harder to interpret with confidence. Inside Morton Thiokol, the concern was not new. Engineers at the Wasatch plant in Utah had already been studying the solid rocket motor field joints. They knew the history of erosion. They knew the significance of blow-by. They knew the joint did not behave as simply as its design intent suggested. But now, the expected cold in Florida forced a narrower question. If the shuttle launched the next morning, would the primary and secondary O-rings seal as required? The launch night discussions began as a technical exchange, not as a public drama. NASA personnel and Morton Thiokol personnel moved into meetings and teleconferences on January 27th, because the forecast temperatures were far below the previous O-ring flight experience base. The Rogers Commission later described phases of the launch night teleconference, including a major second phase beginning at about 8:45 p.m. Eastern Standard Time. The centers and institutions involved reflected the structure of the shuttle program itself: Kennedy Space Center in Florida, Marshall Space Flight Center in Huntsville, Alabama, and Morton Thiokol, the contractor responsible for the solid rocket motors. For the Thiokol engineers, the available evidence pointed toward caution. The O-ring problem was already tied to temperature through the behavior of rubber. Cold O-rings lost resiliency. A seal that might recover its shape quickly at a warmer temperature could respond much more slowly in the cold. That mattered because the field joint had to seal immediately, in the first moments of motor ignition. The question was not whether the O-ring would eventually regain shape in a laboratory sense. The question was whether it would seal in time, under pressure, while the joint was rotating and the motor was producing hot combustion gases. Thiokol's initial engineering recommendation was not to launch below the prior O-ring temperature experience base of 53 degrees Fahrenheit. This was a conservative recommendation, but it was not abstract. It rested on the difference between known flight history and the predicted conditions at Kennedy Space Center. The engineers were saying, in effect, that the program did not have a demonstrated basis for launching colder than that experience. That recommendation placed the burden of proof in a particular place. If the lowest previous O-ring temperature experience was 53 degrees, and the next morning's conditions were expected to be far below that, then the side favoring launch needed to show why the lower temperature would not create unacceptable risk. The difficulty was that the flight record did not provide a neat answer. Previous missions had survived despite O-ring erosion and blow-by. But survival was not proof that the joint had operated with healthy margin. It could also mean that the joint had been damaged without failing completely. This distinction was central to the launch night argument. A record of flights that returned safely can look reassuring from a distance. To engineers examining hardware, the same record can look different. Erosion, soot, and blow-by are not success in the pure design sense. They are evidence that hot gas had reached places it was not supposed to reach. In that context, colder O-rings were not a separate issue from the earlier damage history. They were a condition that could make an already troubling pattern more dangerous. NASA personnel in the discussion heard Thiokol's initial position. Among the NASA figures connected to the solid rocket booster decision environment were Lawrence B. Malloy of Marshall, along with other Marshall and program personnel. Morton Thiokol was represented by managers and engineers who had to translate the technical concern into a launch recommendation. Alan McDonald, who was at Kennedy Space Center, was part of the contractor's launch-side presence. At Thiokol, engineers including Roger Boisjoly and Arnold Thompson were among those who objected to launch under the expected cold conditions. The argument turned on data, but also on how data were framed. Thiokol's engineers could point to the low-temperature boundary of previous flight experience. They could connect cold to reduced O-ring resiliency. They could connect reduced resiliency to delayed sealing during ignition. But the exact behavior of the joint at the next morning's predicted temperatures could not be demonstrated from flight history because the shuttle had not flown those O-rings in that cold. The absence of direct data below 53 degrees Fahrenheit was itself the warning. In a healthy technical decision, uncertainty can be a reason to stop. In a launch decision, uncertainty can also be pulled in the opposite direction, especially when a system has flown before and when schedules, countdowns, and institutional routines are already in motion. The Rogers Commission would later state that the launch decision was flawed and based on incomplete and sometimes misleading information. On the night of January 27th, the shape of that flaw was beginning to appear. Engineering concern was being pressed into a management decision, and the meaning of uncertain evidence was being contested. The teleconference did not simply end with Thiokol's first recommendation. NASA questioned the basis for not launching. The discussion became more strained because the recommendation was not a minor procedural note. A no-launch recommendation from the solid rocket motor contractor challenged the planned morning launch. It required the program to accept delay because of a risk that could not be measured cleanly, but that had a documented history. For Morton Thiokol, the position was difficult. The company had engineers warning against launch below the existing experience base. It also had managers who had to speak formally to NASA. The difference between an engineer's objection and a company recommendation mattered. NASA was not asking only what individual engineers feared. It was asking what Morton Thiokol, as the contractor, recommended. That distinction would become decisive. During the evening, after the initial no-launch recommendation, Morton Thiokol requested time away from the live teleconference. This was the Off-Net Caucus, a private Thiokol discussion that lasted about 30 minutes, though it had initially been requested as a short break. Inside that interval, the debate changed form. It was no longer only Thiokol engineers explaining temperature, resiliency, and flight history to NASA. It became an internal contractor decision about whether to stand by the original engineering recommendation. The importance of that pause is hard to overstate, but it must be kept precise. The source record shows that during the Off-Net Caucus, engineers Roger Boisjoly and Arnold Thompson continued to object strongly to launch. It also shows that after the caucus, Morton Thiokol management reversed the initial no-launch recommendation and sent a written recommendation supporting launch. The final teleconference resumed around 11 p.m. Eastern Standard Time, and Thiokol's written launch rationale was sent by telefax to Kennedy and Marshall. By the end of the night, the formal recommendation had changed. The earlier engineering position had been not to launch below the prior O-ring temperature experience, base of 53 degrees Fahrenheit. The later written recommendation supported launch block EQL'd. Between those 2 points lay the private caucus, the continuing objections of engineers, and the pressure of turning uncertain technical evidence into a yes or no answer. The next morning, visible ice at Kennedy Space Center would show how real the cold had been. But the critical decision had already passed through conference lines, charts, questions, and a management reversal. The night before launch was not a single dramatic instant. It was a sequence, a forecast outside the experience base, an engineering recommendation to wait, challenges to that recommendation, a private caucus, and a final written rationale that allowed the countdown to continue. Inside that sequence, the technical warning did not disappear. It was overruled. The warning, then, did not vanish in the larger teleconference. It moved into a smaller room, away from the NASA conference loop, inside Morton Thiokol's own decision process. That was the Off-Net Caucus on January 23, 1986, a private discussion after Thiokol's initial recommendation had been challenged and before the company returned with a written position that supported launch. This was not a technical problem, suddenly being discovered. By that night, Morton Thiokol engineers had already lived with the field joint concern for months. They knew the history of O-ring erosion, blow-by, and soot. They knew the earlier experience base. They knew that the launch forecast at Kennedy Space Center was far below the lowest temperature at which the O-rings had previously flown. And they knew that their initial recommendation had been clear: do not launch below the prior O-ring temperature experience base of 53 degrees Fahrenheit. The caucus matters because it was the point where the direction changed. In the earlier phase of the launch discussion, Thiokol's engineering position had been carried into the NASA conversation as a no-launch recommendation. The concern was not simply that the weather would be cold. The concern was that cold rubber would be slower to respond at the exact moment the solid rocket motor field joint needed to seal. The joint would experience ignition, pressure, motion, and gap opening. The O-ring would have to recover its shape and seat quickly enough to prevent hot combustion gas from passing through. The cold forecast raised the fear that the seal might not respond in time. Inside the Off-Net Caucus, that concern remained alive. Roger Boisjoly continued to object strongly to launch. Arnold Thompson also continued to object strongly. Their opposition was not a general unease about winter weather. It was tied to the same field joint behavior that had been documented, debated, and warned about within Morton Thiokol before STS-51L. Boisjoly had already written, months earlier, about the potential failure criticality of solid rocket motor O-ring erosion. Thompson, like Boisjoly, was part of the engineering side pressing the risk of the launch conditions. The private caucus was expected to be short, but it lasted about 30 minutes. That duration is important in a quiet way. It suggests the reversal was not automatic and not merely procedural. The people inside Thiokol were trying to resolve a problem that had become both technical and institutional. They had to decide whether the available data justified holding firm against launch, or whether the evidence could be framed as acceptable for flight. The decision environment included several Morton Thiokol figures, whose names later became connected to the launch night record.
Robert K. Lund was part of Thiokol management. Joseph Kilminster was a senior
Thiokol official involved in communicating the company's position.
Jerry Mason was another management figure in the decision environment.
Alan McDonald, at Kennedy Space Center, had been part of the Thiokol presence connected to the launch.
Arnold Thompson and Brian Russell
Were among the engineering voices associated with the technical concern. Jerry Burns and C.G. Wiggins were also part of the Morton Thiokol side of the broader launch decision setting. Those names matter not because every person played the same role, but because the decision was not made by an abstract organization.
It passed through specific offices,
Specific lines of authority, and specific people standing between engineering uncertainty and operational commitment.
The Off-Net Caucus
Was where Morton Thiokol had to turn its internal disagreement into a single external recommendation.
the strongest contrast in the record
Is between the continuing objections from engineers and the later management position.
Boisjoly and Thompson did not withdraw their concern. The technical warning remained.
But after the caucus, Morton Thiokol management reversed the initial no-launch recommendation.
The company then returned to the teleconference with a launch rationale.
That reversal has become one of the central episodes in the history of Challenger because it shows how an engineering warning can be altered without being solved.
The temperature did not change. The O-ring material behavior did not change. The known history of erosion and blow-by
Did not change.
What changed was the official recommendation.
The final written recommendation supported launch.
That point must be held carefully.
The source-grounded fact is not simply that some people were worried or that some people later regretted the decision.
The formal result of the
Thiokol process that night was a written recommendation that allowed the launch to proceed.
The initial engineering recommendation
Had said not to launch below the previous O-ring temperature experience base.
after the Off-Net Caucus.
Morton Thiokol's written position supported launch.
In a technical organization,
Writing matters.
a verbal disagreement can remain in the room.
An objection can be remembered by those who heard it. But a written recommendation travels.
It becomes the document that can be
Faxed, filed, cited, and used as the official basis for action.
On January 27th,
After the caucus, Thiokol's written launch rationale was sent by telefax to Kennedy and Marshall.
the teleconference resumed around
11 o'clock Eastern Standard Time, and the no-launch recommendation had become a recommendation to launch. This did not mean that the engineering concern had been answered in the deeper sense.
The concern was about whether the O-rings
Could seal reliably under conditions far colder than prior flight experience.
The available flight history did not provide an example at the predicted temperature.
The caution from the engineers was that the program would be moving outside the known base.
But the final document did not stop the countdown. It supported proceeding.
The Off-Net Caucus therefore sits at the center of the launch night decision for a reason. It was the point where the company responsible for the solid rocket motor moved from resistance to concurrence. NASA personnel had questioned Thiokol's recommendation.
Thiokol went off the line. Its engineers continued to oppose launch. Then management returned with a different answer.
The Rogers Commission later described the launch decision as flawed and based on incomplete and sometimes misleading information.
The Off-Net Caucus
Is one of the places where that flaw becomes visible.
It shows not a clean technical resolution,
but a narrowing of disagreement into a final managerial position.
It shows how uncertainty was converted into acceptance.
And it shows how the official record sent upward and outward could differ from the unresolved engineering objections still present inside the contractor's discussion.
For Boisjoly and Thompson,
The issue remained the behavior of the joint under cold conditions.
the aft field joint was not a passive seam.
At ignition, the tang and clevis assembly would respond to pressure and movement. The putty, the primary O-ring, and the secondary O-ring were part of a system that had to prevent hot gases from escaping.
Prior flights had already shown that the system could suffer erosion and blow-by.
Cold added another risk, reduced resiliency.
A slower O-ring response
Meant less margin in the brief, violent opening moments of solid rocket motor ignition.
for management.
The caucus required a yes or no answer to a launch question that had no complete experimental certainty. But the final answer carried consequences beyond the room. Once Morton Thiokol reversed itself, the launch decision network received contractor concurrence rather than contractor opposition. The continuing objections of individual engineers did not become the controlling message. That distinction would matter deeply. In the launch decision chain, what was known by engineers was not always the same as what was transmitted to senior decision-makers. The caucus produced a formal recommendation, but it also left behind an uncomfortable separation between the written position and the dissent that had preceded it. The launch would proceed with a document supporting flight, while the strongest warnings remained largely inside the path that produced that document. By the time the discussion ended, the cold weather at Kennedy Space Center was still there. The boosters were still on the pad. The O-rings were still subject to the same mechanical limits. The countdown could continue because the official recommendation now permitted it. But the decision had not erased the earlier evidence. It had only changed which part of the evidence would travel forward with authority. From here, the question widens. If engineers had objected, if a launch constraint had existed, if waivers had been repeatedly granted, and if the contractor's own recommendation had changed during a private caucus, then the next issue is what the senior levels of NASA actually heard. The Challenger decision was not only a story of cold rubber and a reversed recommendation. It was also a story of communication, which warnings moved through the system, which ones were softened, and which ones never reached the people who might have asked harder questions before morning. The warning, by then, had passed through several filters. It had begun as physical evidence on earlier boosters, then as engineering concern, then as memoranda, then as a launch constraint, then as a launch night recommendation not to fly below the known O-ring temperature experience base. In the Off-Net Caucus, that recommendation changed, but the change itself did not mean that every part of the warning traveled upward with equal force. This was one of the central findings of the Rogers Commission. The launch decision for STS-51L was not made with a complete and stable picture of the risk. The Commission stated that the decision was flawed and that it was based on incomplete and sometimes misleading information. That conclusion matters because it shifts part of the story away from a single conference call and toward the structure that carried information through NASA. NASA was not one room. It was a network of centers, offices, managers, contractors, and formal levels of responsibility. Kennedy Space Center in Florida was the launch site, where Challenger stood at Launch Complex 39B in the cold. Marshall Space Flight Center in Huntsville, Alabama, had major responsibility for the solid rocket boosters and their motors. Johnson Space Center in Houston, Texas, was central to shuttle flight operations. NASA headquarters stood above the field centers in the agency's larger management structure. Inside that network were officials whose titles and responsibilities placed them at different points along the decision path. Jesse Moore, Arnold Aldrich, and James A. Thomas were among the senior NASA officials connected to the shuttle launch decision environment. At Marshall, Lawrence B. Malloy was the solid rocket booster project manager, the official who had repeatedly waived the launch constraint connected to the O-ring issue. Stanley Reinartz, Judson Lovingood, George Hardy, William R. Lucas, George Kingsbury, and Cecil Houston were also part of the wider NASA management and technical decision network described in the record surrounding the accident. The crucial point is not simply that many people were involved. It is that the information they had was not the same. The Rogers Commission found that Level 1 and Level 2 NASA officials were not told about the launch constraint on the solid rocket motor field joint O-ring problem. They were not told the reasons for that constraint. They were not told that the constraint had been repeatedly waived before STS-51L. In an organization built on formal reviews and structured authority, that absence was not a small omission. A launch constraint was not casual language. It was a formal signal that a problem had possible flight safety significance. If senior officials did not know it existed, then they could not ask why it existed. If they did not know it had been waived, they could not ask why waiver had become routine. The Commission's finding also shows why the history of the O-rings mattered so much. The concern on the night before launch was not an isolated debate about one cold morning. It rested on a record. Earlier erosion, blow-by, soot, and damage observed after prior shuttle flights. Significant concern after STS-51C in January 1985 and STS-51B in April 1985. The launch constraint placed after STS-51B on STS-51F and later flights, and the internal Morton-Thiokol warnings during the months that followed. This was the context that made the cold forecast so serious. But context only affects a decision if the people responsible for the decision actually receive it. At Kennedy Space Center, the countdown machinery was pointed toward launch. At Marshall Space Flight Center, the booster issue had been reviewed, argued over, and managed through waivers. At Morton Thiokol's Wasatch plant in Utah, engineers had warned that the O-ring seal system was not behaving as intended. At Johnson Space Center and NASA headquarters, senior officials depended on the information passed through established channels. The weakness identified by the Commission was that the channels did not carry the full warning upward. That kind of failure can appear quiet from the outside. No alarm bell has to sound and then be ignored in public. No single person has to announce that vital information is being withheld. Instead, the record can become thinner as it moves. Technical uncertainty can be translated into managerial confidence. A prior anomaly can become acceptable because earlier flights survived. A launch constraint can remain known to one level of management but invisible to another. A waiver can become a procedural step rather than a renewed question about risk. This is why the names in the decision network matter. Lawrence B. Malloy's role as Marshall Solid Rocket Booster Project Manager placed him close to the booster hardware issue and the repeated waivers. George Hardy, also at Marshall, was part of the technical and management discussion around the solid rocket motor concerns. William R. Lucas, director of Marshall Space Flight Center, stood within the center leadership that had responsibility for the booster program. George Kingsbury and other Marshall officials were part of the organization in which the O-ring problem was being managed. Cecil Houston, at Kennedy, was connected to launch processing and the information environment at the launch site. Jesse Moore and Arnold Aldrich occupied senior positions in the shuttle management structure. James A. Thomas was part of the Kennedy launch decision chain. Stanley Reinartz and Judson Lovingood were part of the Marshall management structure connected to shuttle propulsion and program responsibility. The Commission's concern was not that every senior official had to know every engineering detail of tang, clevis, putty, joint rotation, and O-ring resiliency. Large technical organizations cannot operate that way, but certain kinds of information are different. A launch constraint exists because a problem has crossed a threshold. Repeated waivers show that the threshold has not gone away. A contractor's initial no-launch recommendation, especially one tied to a forecast outside the known experience base, is not merely a technical footnote. It is the kind of information that can change the questions asked by senior decision-makers. If a Level 1 or Level 2 official had been told that the O-ring problem had previously led to a launch constraint, the discussion could have changed. If that official had been told that the constraint had been waived repeatedly, the discussion could have changed again. If the full history of erosion, blow-by, temperature sensitivity, and engineering objection had been presented with its original force, the decision environment would not have been the same one described after the fact. The Rogers Commission did not need to claim that every missing communication would automatically have stopped the launch. Its point was more precise and more troubling. The decision that allowed Challenger to fly was made without the full record reaching the senior levels responsible for accepting the risk. In a program where thousands of components had to work at once, risk could not be judged honestly if the evidence was fragmented on the way up. This also helps explain the phrase incomplete and sometimes misleading information. Incomplete information leaves out necessary facts. Misleading information can create confidence that the full record does not support. Together, they can make a hazardous condition look like a manageable one. The O-ring issue had not been solved. The joint design remained sensitive to temperature, physical dimensions, material behavior, reuse, processing, and dynamic loading. The cold at Kennedy Space Center still threatened O-ring resiliency. But the official path toward launch carried forward a rationale that said launch could proceed. By the morning of January 28, 1986, the management decision had hardened into action. Challenger stood on the pad with its external tank and twin solid rocket boosters. The right booster aft field joint, the same region at the center of the unresolved concern, was no longer an item in a teleconference. It was part of a live vehicle, loaded into the violent sequence of ignition. The warnings that did not fully reach the top were still present in the hardware. They were present in the cold rubber, in the field joint geometry, in the record of prior erosion, and in the history of waivers. At launch, the communication system would no longer matter as much as the seal itself. The question that had moved through memos, meetings, and management channels would be answered in the first seconds of flight.
By the time Challenger left
Launch Complex 39B, the unresolved question was no longer moving through a chain of people.
it was moving through the vehicle itself.
The right solid rocket booster aft field joint, cold through the night and then exposed to the sudden violence of ignition, became the place where the earlier warnings entered the flight record.
The Rogers Commission would later reconstruct the opening seconds,
Not as a single instant of failure, but as a short, visible sequence. It began almost immediately after solid rocket motor ignition.
in the film record.
Smoke was observed from the right solid rocket booster aft field joint area between about 0.678 and 2.500 seconds after ignition.
The smoke appeared in repeated puffs.
At roughly 3 puffs per second.
That timing mattered.
The field joint was supposed to seal under pressure as the motor came alive. The primary O-ring, backed by a secondary O-ring, was part of a system meant to prevent hot combustion gases from escaping through the tang and clevis joint.
But the earliest smoke
Showed that something was already wrong in the aft field joint area of the right booster.
The Commission's record placed
The origin in the same region that had been at the center of the pre-launch concern, the joint where low temperature, joint movement, and O-ring response were no longer abstract engineering terms. In these first seconds, Challenger still looked, to the public eye, like a normal launch.
the vehicle rose from Kennedy Space Center,
driven by the 2 solid rocket boosters and the Space Shuttle main engines.
The sound and brightness of liftoff
Could overwhelm any sense of fragility.
but in the Commission's reconstruction,
The evidence of leakage was there almost at once.
the smoke puffs came from the right
Booster aft field joint area, the region later tied to the failed pressure seal.
Then the visible smoke stopped.
That pause is one of the important details in the accident sequence. The absence of continuing visible smoke did not mean the joint had become healthy.
The Commission's account explains the early smoke
as part of the seal failure evidence, but the later sequence shows that the breach was not gone.
The launch environment changed as the shuttle climbed. Aerodynamic forces,
Vibration, motor pressure, vehicle motion, and the continuing burn of the solid rocket booster all acted on hardware that had already shown a sign of distress.
for nearly a minute, the flight continued. Challenger climbed through the Florida sky.
Inside the vehicle, the crew and systems were still in ascent.
Outside,
The right solid rocket booster remained attached to the external tank by struts, including the region near the aft field joint that earlier analysis had identified as important.
the Commission had reported that the
310-degree strut region could increase local joint gap opening by about 10 to 20%.
the failed flame location
Was later estimated around 305 to 307 degrees.
In other words,
The local geometry and loading around the joint were not incidental background.
they were close to the place where the physical failure was found.
At about 58 seconds into flight, a flame from the same right booster joint area became clearly visible. This was the transition from a brief early sign to an active, destructive event.
The flame was no longer just
An indication of smoke escaping during the ignition transient.
It was evidence of hot
Gas burning through from the solid rocket booster, outside the path where that energy was supposed to remain contained. A solid rocket motor is not a machine that can be throttled down or shut off once its propellant is burning in flight. Its internal pressure and combustion are part of the ascent plan. The danger was that combustion gases, escaping through a joint, could attack surrounding structure. The Rogers Commission's physical evidence after the accident matched that film record. Recovered fragments from the right solid rocket booster aft joint showed large burn-through holes around the joint circumference. The reported region extended from about 291 degrees to 318 degrees. The failed flame location was estimated around 305 to 307 degrees. These measurements gave investigators a physical map of the breach. They tied the visible flame in flight to a specific zone in the joint hardware recovered after the loss. The numbers are technical, but they are not sterile. They locate the failure on a circular joint around a real piece of recovered booster structure. They show that the accident was not caused by a vague malfunction somewhere in the shuttle stack. The Commission traced it to the aft field joint of the right solid rocket motor, to a pressure seal that did not perform its required function, and to burn through in a defined region of the joint circumference. The earlier chapters of this story have followed warnings before launch, prior O-ring erosion and blow-by, the launch constraint and waivers, the internal Morton-Thiokol memos, the cold weather teleconference, the reversed recommendation, and the incomplete communication to higher NASA levels. In the 73 seconds of flight, those warnings became visible in a different archive. Not in memoranda, not in meeting notes, not in management testimony. In smoke, flame, recovered metal, and the geometry of a burned-through joint. The sequence is also important because it resists a simplified picture of disaster as one sudden surprise. Challenger did break apart 73 seconds after liftoff, but the commission record shows a developing failure after ignition. Smoke appeared in the first seconds. A flame became clearly visible at about 58 seconds. The final breakup came after the breach had already been present and worsening. The catastrophe was sudden to those watching, but the evidence shows a progression. This does not make the event less tragic. It makes it more traceable. The accident investigation had to work from film, telemetry, debris recovery, materials analysis, and the engineering history of the solid rocket motor joint. It had to connect what was seen during ascent with what had been known before launch. The right booster aft field joint was not an unknown system. It was a system whose behavior under cold temperature and dynamic loading had already been questioned. Its O-rings were not unfamiliar parts. They had been discussed in relation to resiliency, erosion, blow-by, pressure actuation, and the need to seal quickly during the ignition transient. In the first seconds of STS-51L, the joint had to do exactly what engineers had been worried it might not do. It had to seal instantly, under conditions colder than the previous O-ring temperature experience base. The film record of smoke showed that the required containment had failed at the very beginning of flight. The later flames showed that the failure had not remained harmless or self-limiting. There is a quiet force in the Commission's chronology because it lets the evidence speak in order. Ignition. Smoke from the right aft field joint area. A period in which the vehicle still climbed. A visible flame from the same region at about 58 seconds. Burn-through holes found in recovered joint fragments from about 291 to 318 degrees. An estimated failed flame location around 305 to 307 degrees. Then the loss of Challenger and her crew at 73 seconds after liftoff. Each point narrows the story. The disaster was not explained by speculation about an external act. It was not located in an undefined weakness of the shuttle as a whole. The central mechanism was in the right solid rocket motor aft field joint, where a pressure seal failed and hot gases escaped. And yet, the technical precision of that conclusion does not separate it from the organizational history. It depends on it. The seal that failed had been the subject of earlier evidence, earlier concern, and earlier decisions. The joint fragments recovered after the accident were not just debris. They were the final physical record of a risk that had been documented before the vehicle left the pad. By the end of the flight, the question had changed. Investigators no longer had to ask whether an O-ring field joint problem could become catastrophic. Challenger had answered that in the most devastating way possible. The remaining work was to determine, with discipline and public accountability, how the known warnings had been handled, what the official cause would be, and why the system designed to manage risk had allowed the launch to proceed. That work would fall to the Presidential Commission, chaired by William P. Rogers, where the technical failure and the warning signs before launch would finally be examined together. The investigation began where the flight had ended, with pieces of hardware, film records, telemetry, testimony, and a question that could no longer be treated as theoretical. Challenger's loss had turned the field joint concern into a national inquiry. The warning signs that had moved quietly through engineering channels before launch now had to be reconstructed in public under the authority of the Presidential Commission chaired by William P. Rogers. The commission brought together figures whose names carried unusual weight in American aviation and spaceflight. Among its members were Neil Armstrong, the first person to walk on the moon, Sally Ride, the first American woman in space, Chuck Yeager, whose test pilot career had become part of the history of supersonic flight, and Richard Feynman, the physicist whose role in the inquiry would become widely remembered. Their task was not simply to describe a breakup in the sky. It was to determine why the vehicle had been allowed to launch with a known history of concern in the solid rocket motor field joints, and why the final objections before flight had not stopped the countdown. The Commission's central technical conclusion was direct. The accident was caused by the failure of the pressure seal in the aft field joint of the right solid rocket motor. That finding placed the cause in the same mechanical system that engineers had been discussing before launch: the tang and clevis joint, the zinc chromate putty, the two rubber O-rings, and the need for the seal to respond instantly as the booster came alive. The failed area was not a mystery unrelated to earlier concerns. It was the aft field joint of the right booster, the same class of joint whose behavior had produced erosion, blow-by, soot, memos, constraints, and launch night debate. The Commission also addressed another question that had to be answered in an event of this magnitude. It found no evidence of sabotage at the launch pad, or during the pre-launch or launch processes. That conclusion mattered because it narrowed the explanation back to the system itself. The disaster did not require an outside act to explain it. The record pointed to hardware behavior, environmental conditions, prior evidence, engineering judgment, management decisions, and communication failure. The cause was not hidden in an act of interference. It was visible in the history of the joint. In the Commission's account, the fatal mechanism began with the failure of the seal to prevent hot combustion gases from escaping the right solid rocket motor. Earlier film evidence had shown smoke from the right booster's aft field joint area within the first seconds after ignition. Later in flight, a flame became clearly visible from that same region. Recovered fragments from the aft joint showed large burn-through holes around the circumference in the area later associated with the failure. These pieces of evidence joined the physical and visual record to the Commission's conclusion: the pressure seal had failed, and once the escaping gases found a path, the mission could not survive. But the report did not stop at the physical cause. It also examined why the warning signs before launch had not been enough. The solid rocket motor field joint, as the Commission described it, was unacceptably sensitive to temperature, physical dimensions, material behavior, reuse, processing, and dynamic loading. That phrase carried a large implication. The joint was not a simple part that had failed in one isolated way. It was a system in which small differences in gap, rubber response, cold exposure, previous use, and ignition loads could combine at the worst possible moment. This was why the pre-launch weather had mattered so much. Cold O-rings were less resilient. A compressed O-ring at 75 degrees Fahrenheit returned to shape about 5 times faster than one at 30 degrees Fahrenheit, according to the Commission's comparison. On the night before launch, engineers were not objecting to cold as a general discomfort or a vague concern. They were objecting because the seal depended on rubber moving quickly enough to close a gap as the booster pressurized and the joint rotated. If the O-ring was too slow, hot gas could pass before the seal was fully made. The Commission's work gave official shape to a pattern that had been visible before Challenger. Earlier flights had shown O-ring erosion, blow-by, or soot. After STS-51B, the issue was serious enough that a launch constraint was placed on STS-51F and subsequent flights, including STS-51L, yet the constraint was repeatedly waived by Marshall Solid Rocket Booster Project Manager Lawrence B. Malloy. Just as important, the Commission found that Level 1 and Level 2 NASA officials were not told about the launch constraint, the reasons behind it, or the series of waivers before Challenger's launch. That finding is one of the quietest and most consequential parts of the record. It shows how a risk can be formally recognized and still fail to reach the right level of attention. A launch constraint should have been a signal. Repeated waivers should have been a stronger signal. Prior erosion should have strengthened it again. But the information did not move cleanly through the organization. By the time senior officials were making and accepting launch decisions, the full history of the field joint concern had not been placed before them in the way the danger required. The same pattern appeared in the final hours. On January 27, 1986, Morton Thiokol engineers and NASA personnel discussed the forecast temperatures at Kennedy Space Center. Thiokol's initial engineering recommendation was not to launch below the previous O-ring temperature experience base of 53 degrees Fahrenheit. During the Off-Net Caucus, engineers Roger Boisjoly and Arnold Thompson continued to object strongly, but Morton Thiokol management reversed the initial no-launch recommendation and sent a written recommendation supporting launch. The Commission described the launch decision as flawed, based on incomplete and sometimes misleading information. That judgment did not turn the tragedy into a simple story of one person or one meeting. It pointed to a chain. The warning signs had passed through memoranda, task force concerns, constraints, waivers, teleconferences, and management summaries. At each stage, the technical issue remained real, but the organizational handling of it changed its force. Concern became discussion.
Discussion became rationale.
Rationale became acceptance. Acceptance became launch. In that sense, Challenger's final lesson is not divided neatly between engineering and management.
The fatal mechanism was technical.
The failure of the pressure seal and the aft field joint of the right solid rocket motor. But the warning signs before launch were organizational as well as mechanical. They existed in damaged hardware from earlier flights, in the known sensitivity of O-ring resiliency to cold, and Roger Boisjoly's warning that failure to prioritize the field joint O-ring problem could risk losing a flight and launch pad facilities, and in Robert Ebeling's plea for help on the SEAL task force. They also existed in what was not fully communicated upward. The Commission gave the country an official explanation, but the unresolved lesson remains larger than the wording of a finding.
High-risk machines do not fail only when metal breaks or rubber burns.
They fail when evidence is normalized, when exceptions become routine, when a known problem is managed rather than resolved, and when the people with the clearest concerns cannot make those concerns decisive. Challenger left Launch Complex 39B on the morning of January 28, 1986, carrying 7 crew members and the hopes of a public mission. 73 seconds later, the nation saw the visible end of a failure that had been developing out of sight.
The Rogers Commission traced that end back through the hardware and through the decisions.
It found no sabotage, no hidden external act, no explanation more complicated than the one already written into the record before launch.
There had been warnings. They were technical, specific, and repeated.
They moved through cold rubber, field joint geometry, prior erosion, launch constraints, memos, waivers, and teleconferences. The final chapter of the Challenger story is not only that a SEAL failed. It is that the system had been warned about the conditions under which it might fail, and still the shuttle was cleared to fly. That is the lesson left in the archive. In engineering, the most important warning may arrive before anything breaks, and the cost of not hearing it may not be known until it is too late.